11.6, making decisions and predictions. I can use probability to make decisions and predictions.
All right, cool. So the first main idea, we use ratios and proportions to help us make a prediction or help us make decisions on what we're going to do. We surveyed a whole bunch of customers, and we found this result. We found that 125 were pleased, 340 were satisfied, and 35 were unhappy. All your eyes should be up here. We needed to report back to our boss because at our company, which is Target, we serve 500,000 people, and my boss asked me to figure out how many people were unhappy, how many customers were unhappy. I said, boss, I can't call them all. The boss said, figure it out. So I had my intern do a little survey of 500 people, and we found out that 35 out of 500 were unhappy. Boss wants to know how many total are unhappy. What are we using to get there, everybody?
Proportions.
So if 35 out of 500 are unhappy, could we expect that X out of 500,000 are unhappy?
Yes.
And are you able to use this number here to get to the number X?
Yes.
And we use our little bubble method, yes, no?
Yes.
How do we get 1,000 though? How do we figure out that 500 times 1,000 gets us to 500,000? Abhijit.
We divided 500,000.
We divided 500,000 by 500, right? And then whatever we do to the bottom, if we multiply the bottom by 100 out of proportion, we multiply the top by, I meant 1,000. 1,000 and, cool. Do you think our boss is going to be happy that he has 35 or she has 35,000 unhappy customers?
No.
Abby, she's bored one day, so she decides she's going to guess if she can pick the correct card from a deck of cards. What's the theoretical probability that Abby can pick the correct cards or she can guess what card she's going to pick? What's the theoretical probability, everybody, on the count of 3? 1, 2, 3.
1 out of 52.
1 out of 52. But Abby knows she's going to do it 1,000 times. So could we use the proportion, a proportion, to help us figure it out?
Yes.
If Abby knows it's going to happen 1 out of every 52 times, theoretically speaking, she can set up a proportion to figure out how many times it should happen. Should. Everyone say should.
Should.
Every 1,000 times. We figured out that 52 times 19 is approximately 1,000. And so we multiply the top by 19 as well. We cool with that?
Yes.
I'll try to shorten this video for you right now. Fair games. This was a struggle for us. The struggle for us, I think, was two things. One, we didn't know what to do to help us solve the problem. We needed to, when you read through problem number 3, we needed to create a, because we needed to know what? What did we need to know? We need to know what could happen in flipping the coin between Triana and Sid. Once we figured out the sample space, the second problem then was answering the question. And the question was, Sid wins the game if exactly one coin lands heads. And how many situations right here in my sample space does one coin land heads?
2.
Here and here. Is it a fair game?
Yes.
Is it a fair game?
Yes.
Fair means what?
Equal.
Equal. So Sid's sore loser, remember? She's a sore loser. So she wanted to win more than Triana. So she changed the rules and she said, okay, instead of having just one, instead of having, what do we say up there? Instead of saying that, what was the, I forgot. Exactly. Instead of saying exactly, she's saying that at least. We changed the wording from exactly to at least, right?
Yes.
And we came up with our sample space right here. And we figured out that Sid wins how many times?
3.
Wording makes a difference, but before you even get to the wording, you have to understand what you need to solve the problem. In this case, we needed the outcomes. We needed the sample space. Yes, no?
Yes.